A catastrophic mid-air engine failure can often trace its origins back to a tiny component, specifically a ring of metal only a fraction of an inch thick giving out under extreme pressure. Before we tear down the anatomy of this exact component, make sure to like and subscribe for more aviation maintenance guides. Look at this 3D exploded view of a piston inside its cylinder. The piston rings are the absolute boundary line. They seal the exact clearance between the piston and the cylinder wall. Their entire purpose is to trap expanding, high-pressure combustion gas above the piston head, while simultaneously blocking crankcase oil from seeping up from below. To manage those dual threats, aircraft engines divide the workload across 3 distinct zones on the piston. At the very top, we have the compression rings. Immediately below them are the oil control rings, and down near the bottom of the piston skirt sits the oil scraper ring. Because these 3 layers operate together to maintain total system pressure, a single fracture or blockage in any one ring immediately compromises the entire engine block's ecosystem. This 2D cross-section details the top piston ring groove. The compression rings located here take the brunt of the explosive force. They physically block combustion gases from escaping past the piston head during the power stroke. While standard compression rings are rectangular, many engines utilize a wedge-shaped or tapered face. Notice how the tapered face presents a much narrower bearing edge to the cylinder wall. This precise geometry reduces surface friction, allowing the piston to glide efficiently while still maintaining a perfectly gas-tight seal. Most of these rings are machined from high-grade gray cast iron because it holds its shape perfectly under pressure. However, in specific high-stress engines, mechanics will use chrome-plated mild steel for the top compression ring because it withstands far higher peak combustion temperatures. This logic chart dictates a strict rule of material pairing. Chrome compression rings are only safe to use with steel cylinder walls. If you match a chrome piston ring with a chrome-plated cylinder wall, the identical metals will generate extreme friction, bind together, and tear the engine apart from the inside. Selecting the exact shape and metallurgical match for your compression ring dictates whether the engine flies safely or destroys itself within minutes of ignition. Moving down the piston, this cross-section shows the middle grooves housing the oil control rings. Unlike the compression rings above, these regulate the exact thickness of the oil film applied to the cylinder wall. If the oil control rings fail to regulate that film, excess oil slips up into the combustion chamber and burns. That burning oil leaves a thick coating of carbon on the chamber walls, the piston head, and the spark plugs. This carbon crust causes valves to stick open, triggers detonation, and guarantees spark plug misfires. To mechanically prevent that failure chain, holes are drilled directly into the bottom of the oil control ring grooves, or in the lands immediately next to them. These tiny pathways allow surplus oil scraped from the wall to drain safely back down into the crankcase. Finally, at the lowest groove on the piston skirt, we find the oil scraper ring. Depending on the exact engine design, this ring is installed with its beveled face oriented to physically push a concentrated wave of surplus oil, either up toward the control rings or back down to the crankcase on the return stroke. The top rings contain the explosive gases, while these lower rings manage continuous fluid dynamics. Together, they keep the engine lubricated without letting it drown in its own oil. When breaking down an engine, your visual inspection begins with a physical check of every ring. You must compress them by hand to verify their outward springiness, ensuring they will expand to fit snugly against all points of the cylinder wall. Next, inspect the very bottom layer. You are looking specifically at the condition of the scraper ring's beveled edge. A dull or flattened edge means the ring can no longer physically sweep the oil. Take a close look at this generated view of a mechanic inspecting the middle grooves. You must actively shine a light into the tiny drain holes behind the oil control rings. Black carbon buildup clogging these holes is a guaranteed point of failure that will trap oil above the piston. Let's test your recall. Look at this spec sheet. If an FAA-certified manual states that your replacement cylinder wall has a chrome finish, what specific material must you select for the top compression ring? The answer is cast iron or mild steel, never chrome. Every visual inspection and replacement choice you make on the bench must map directly back to the required specifications in the engine manual. A microscopic amount of misdirected oil at the piston skirt eventually evolves into a total loss of compression and an in-flight engine failure. Mastering the exact functions of these 3 ring types prevents that outcome. Your safety checklist comes down to 4 precise validations. Check the top compression ring for a snug wall fit. Verify exact material pairing between the ring and cylinder. Confirm the middle drain holes are entirely clear of carbon. And check the bottom scraper ring for a sharp bevel and proper upward or downward orientation. Long-term engine reliability relies entirely on the perfect compartmentalization of gas and oil. Keep these boundaries intact and always trust the FAA-certified engine manuals before you close up the block.